So for the plastic moment capacity, which is the moment required to form the plastic hinge, can easily be computed from the consideration of the corresponding stress distribution. As you remember, no, from the previous discussion, diba? As this load progresses, there will comes a time na maabot siya sa plastic moment, no? Then hangtod nga as further increase in the load, no, the beam will collapse. Then especially kaning sa steel, no, naa siya gitawag nga plastic hinge nga in the center, no, diri mo collapse ang beam, no. So how to compute for the plastic moment, no, capacity of the beam. So this figure represents the direction or of the stresses. So from figure below, the compressive and tensile stress resultants are shown, where A sub C is the cross-sectional area subjected to compression and A sub T represents the area in tension. These are the areas above and below the plastic neutral axis, which is not necessarily the same as the elastic neutral axis. Since the beam is already in the plastic neutral axis, so the shape, no, of the stresses is like this, no, rectangular siya na siya. So this is the plastic neutral axis, and this top, no, or upper of the neutral axis is the compression side of the section, and the lower side of neutral axis is the tension, no, of the section. So this C, since this is symmetrical, no, the shape is symmetrical, so you can expect now from equilibrium of forces, the compression is actually equal to tension, which is the same in reinforced concrete, diba? So this C, the force, no, the concentrated force C is actually equal to the area, no, cross-sectional area subjected to compression times the yield strength is equal to the area, cross-sectional area subjected to tension times the yield strength. Then since yield strength is on both sides, you can just cancel this one, so that the areas of both the compression and tension side is actually equal. Thus the plastic neutral axis divides the cross-section into two equal areas. For shapes that are symmetrical about the axis of bending, the elastic and plastic neutral axis are the same. So especially no, for symmetrical shape, no, so the elastic and plastic neutral axis are the same, which is at the middle, no, mid height of the shape. Plastic moment M sub P. The plastic moment M sub P is the resisting couple formed by the two equal and opposite forces. Or this one, how to generate or derive this formula is just actually kung imo na siyang i-derive, you can moment, no, you can actually moment at the compression side of the section or at the tension side, no. Kung mag-moment ka diha, okay, atong ikuan ha, how to generate this kani siya nga formula. Kana siya. So actually kana siya is equal to this one. You can actually moment at the tension side of the section, no. Kung mag-moment ka diri, you can actually moment no sa tunga, no, center of the tension side. So kung mag-moment ka diha, you have the force which is equal to the moment at the tension side is actually equal to the C times the moment arm, di ba? But C is equal to the A sub C, which is the area subjected to compression times the yield strength. This is just force times the moment arm, which is equal to A, as can be seen in this figure, no? So that the M sub P, or the plastic moment, is equal to this one, di ba? The yield strength times the area subjected to compression times the distance. Or you can actually pareha naman siya. If try to moment at the compression side, kung moment ka din actually pareha. You have the plastic moment. The M sub P is equal to the area subjected to tension times the yield strength times the distance, no? Or the moment arm, which is equal to A. So, actually, mura na siya. Is equal to A over 2. This A over 2, since this area subjected to compression and tension is actually the same and just half of the total cross-section of the section. So, mo na siyang A over 2 na siya. Diba? So, can also be written as F sub Y times A over 2, which is, since half, no? This one is half of the cross-section of the steel times the A, no? Or the A is the distance between the centroids of the two half areas, no, between the compression section and the tension section. Or this kani siya na term, or A sub 2 times A is equal to Z, or this plastic moment can also be written as the yield strength times the plastic section modulus, or Z. Z is equal to A sub 2, A over 2 times the distance between the centroids of the two half areas, no? So we have this example. Let's try to answer this example. Now, for the built-up shape shown in figure 5.6, determine the elastic section modulus S and the yield moment M sub Y, and the plastic section modulus Z, and the plastic moment M sub P. For B, plastic section modulus Z and the plastic moment M sub P. Bending is about the x-axis, no? So your axis is x, about the x-axis. The steel is A572 grade 50. So meaning grade 50, your F sub Y is actually equal to 50 KSI, no? So we try to solve for the elastic section modulus S and the yield moment. So first is, if you try to look at the section is actually symmetrical, no? Then because of symmetry, the elastic neutral axis, the x-axis, is located at mid-depth of the cross-section, which is the location of the centroid. So since of the kinesia is symmetrical, no? So the neutral axis is actually just the mid height, no, of the beam. Of the section. So man siya neutral axis, diba? So the moment of inertia of the cross-section can be found by using the parallel axis theorem, and the results of the calculations are summarized in table. So this one, no, I believe you already learned this one or encountered this one in your static of rigid bodies. So kabalo na siya na mo, how to get the moment of inertia by parallel axis theorem. So you have these two flange, diba? The upper and lower flange. So to get this is built up section, through different sizes of plates, and you have two flanges at sizes 8 inches and 1 inches. So how to get the individual moment of inertia for flange is actually this one is equal to 8 inches times 1 inch cube over 12. The same with the lower flange, no? So kani siya, the upper flange and the lower flange. That one, the I is 8 inches times 1 inch cube over 12. So that is 0.666 infinity. Then the area is the area, no? 8 inches times 1 inch. Then D, this is actually distance from neutral axis to the centroid of the flange, no? So try to look at the figure. Half of this is 1 foot, diba? So this is 12 inches, 6 inches, half of 12, 6 inches plus half of 1 inch. So that is 6.5 distance, no? And the other flange actually is the same, no? For the lower flange, muna siya pareha. So that the value of the I plus AD squared is this one, no? For the web, this one, the web. Since ang imong neutral axis is at the middle, no? So your D actually in here is the same, no? Sa middle, yapan siya. So, actually, wala kay value for your D. So, in the area is like, giana lang siya. But, actually, you have the area. But since you don't have the D because neutral axis nimo at the center, if you try to get the D, wala kay makuha nga distance. So, meaning, 0 or D. So, dili nimo siya ma-count. Only the I will be accounted lang sa value for I plus AD squared. So, the sum up this one is this value, no? 749.4. And to get for the elastic section modulus, which is equal to I over C, C is the distance from the centroid to the extreme fiber, di ba? So, half of the where is the neutral axis, di ba? Sa tunga. So, half of that plus this 1 inch. So, 6 plus 1, no? 7 inches. So, the value for your elastic section modulus is 107 cubic inch. And for the yield moment is actually, if you remember sa discussion kanina, okay, the yield moment is actually equal to the yield strength times the elastic section modulus. So since the kind of steel is given with grade 50, so automatic your yield moment is this yield strength times the elastic section modulus. So 50 times 107 or 446 foot kips, no? So your answers are this one. For letter B, we are required to determine the plastic section modulus and the plastic moment. So, because, because the shape is symmetrical about the x-axis, this axis divides the cross-section into two equal areas and is therefore the plastic neutral axis. So, the elastic and the plastic neutral axis are the same lang sa tunga. So the centroid of the top half area can be found by the principle of moments. So taking moments about the x-axis, the neutral axis of the entire cross-section, and tabulating the computations, we get this y bar, or the value of the centroid of the half. No? We consider the centroid of the top half area, no, of the section. So you have this flange, so you will only consider ang top half or lower half. So consider ang tunga lang, no? So you have the area of the flange, which is 8 times 1, so 8 square inch. The centroid of the flange is 6.5, and for the web, the area is given mo tong dimension, diba? You have this 1 foot times 1/2 inch, no? So that is 12 times 0.5, 6. Half of that is the area. So manang 3, no? So 3. And the centroid of the web is half. So this is, kataas is 12 inches. So half is 6. Again, half of 6 is 3 inches. So manang 3. Then multiply, no? Area times the centroid. So, actually, naman siya sa statics of rigid bodies. I believe you you understand this one. Then sum up the areas and the product of the area times the centroid, no? So you get the centroid of the half, no, of the section equal to 5.545 inches. So this figure okay. So you have the value of your y bar, no, which is the centroid of the upper half and also of lower half, since the same naman siya, diba? Because of symmetry, no? So the same value of your y bar. So the figure above shows that the moment arm of the internal resisting couple is twice of this centroid, no, from the neutral axis. So manang 2 times 5.545 is 11.09 inches. And the plastic section modulus is, if you remember, plastic section modulus is equal to the half of the area times the distance, no? Distance from the centroid of the tension side to compression side. So mo nang half of the area. So the area of this one is 11, no? Total area is 11. No, this is actually 11 inch square. This is actually half naman dahil siya sa section. So times 2 of that is 22. But this one is A over 2 man siya. So still 11 yapon siya. No? Half of the total area times the distance from the centroid of tension side to compression side equal to twice of this centroid from the neutral axis. I mean, from the neutral axis to the centroid of the upper portion or lower tension section of the steel. So that the plastic section modulus is equal to 122 cubic inch. And the plastic moment is equal to the yield strength times the Z. The Z is the plastic section modulus, diba? And the yield strength is given as 50 KSI times the obtained plastic section modulus equal to 122. So that the answer is 508 foot cubes. So these are A answers. For another example, compute the plastic moment M sub P for the shape W10 by 60 of A992 steel. So from the dimension properties tables in part ISC manual, this W10 by 60 has an area of, kung tanaw ninyo sa table, kaning W10 by 60 is, okay, pangitaon sa nato. Pero madugay ta, so nato pangitaon, basta kay pangitaon ni sa manual. Basta kay sa table na siya area nga 17.7 square inch. So half of that is 8.85, no? So the centroid, no, of this shape W10 by 60 can be found in the tables for WT shapes. Actually, these WT shapes are the shapes nga half of wide flange. Pero nagyapan siya sa AISC manual. So these are the shape which are cut from W shapes, no? The relevant shape here, no? We actually divide the area by 2, no? So if you try to look at table for the WT shape, may tao, no? Remember this one, the shape, original shape is W10 by 60. So you'll expect na half of that. Remember this 10 is the depth, di ba? Na siya ang kalalong sa steel element times 60. 60 is the weight, no? So kung atong itunga lugar ni siya, half of the area, so meaning this 10 will become 5, no? And expect na ang 60 mahimong half gyapon. So munang the relevant shape is WT 5 by 30. So if you pangitaon mo sa manual, WT 5 by 30 is, I mean, the centroid, no? So T5 by 30 is equal to 7. Oh my gosh. WT5 by 30. So the So the distance from the outside face of the flange to the centroid is 0.884 inch now from the table. Now, WT 5 by 30. So, kung tanaw mo siya, WT 5 by 30 is, okay, nasa second table, no? WT 5 by 30, the centroid, no, from the outer, or from the upper fiber to the centroid is 0.884. Kani siya, 0.884 inch. So, ikan diri, padong diri, no? And to get the plastic section modulus, or Z, I mean to get the distance, no? From this one, from here to here, kani siya, ikan ani to diri is A, that is equal to the total depth of the steel minus 2 times for the distance from the extreme fiber to the centroid, kanino minus kani siya, and kani minus kani. So that is D minus 2 times 0.884. And this W10 by 60 has this depth of 10.2 inches. So, monang A is equal to 8.432 inches. So that the plastic section modulus is half of the area times this A. No? This result, when rounded to 3 significant figures, is the same as the value given in the dimensions and properties tables. So the plastic moment is equal to the yield strength, which is equal to 50 ksi times the plastic section modulus, 74.62. So muna siyang plastic moment is equal to 311 foot kilopounds.